Now we will discuss our Earth, the third rock from the Sun. The first of the two lectures will cover the formation and composition of Earth. Today we'll discuss both the origin of the solar system and Earth as a terrestrial planet in the solar system. To understand where the Earth comes from, you kind of have to understand where the solar system comes from. We can figure out the age of the solar system in numerous ways. One of the most reliable ways is radioactive dating. The oldest rocks on Earth are shown to be 4 billion years old. This is similar of any other rocks that have been examined radiometrically. From this we can conclude that the solar system must have formed about 4.5 billion years ago. This radioactive dating is a very reliable way of gauging the ages of a particular rock. When I created this slide, it was taken from a textbook, and I found it necessary to both include the last point and make a point of crossing it off. Why, we will see in a moment. First, let's look at the other 2 points. When scientists posit an explanation for how the solar system forms, we have to explain certain observations. We have to explain why it is that planets revolve around the sun very close to the same plane, and why most of them rotate in the same direction as the sun. We will find out later that Venus is an exception to this. However, all the other planets rotate in the same direction as the sun. The last point, which I've crossed out, suggests that our solar system is typical, when in fact this is not actually the case. This point suggests that dense planets, smaller planets, are found close to the sun, and gaseous bodies are found farther from the sun. While this is true in our solar system, there are hundreds and hundreds of extrasolar planets known to date. And the vast majority of these include what are known as hot Jupiters, which are gaseous worlds the size of Jupiter or larger, that orbit very close to their parent stars. This is why I crossed this point out, because presumably whatever formation mechanism is responsible for the formation of our sun and our solar system would also be responsible for the formation of other planetary systems. So it must explain both planets possibly closer to the sun or star, or gaseous worlds closer to the star. The best theory we have thus far is the solar nebula theory. This idea suggests that there was something known as a pre-solar nebula. This is basically just a cloud of gas and dust rotating slowly and perhaps over time it experiences a perturbance which gets it rotating a little bit more quickly. Through conservation of angular momentum, as it rotates more quickly, it contracts, rotates even more quickly. This process goes on until you have a rapidly rotating central bulge surrounded by gas and dust. The central spherical part would be destined to become our sun, and the planets would form out of the cloud of dust and gas that surrounded the sun. Planets are thought to condense out of the cloud of gas and dust, with the volatile gases being able to condense farther out. On the surface, this seems to explain why gaseous planets would form further from the star. But again, extrasolar planets suggest that gaseous worlds orbiting close to the star may actually be the rule rather than the exception. Current research suggests that these gaseous worlds may have migrated, perhaps forming farther from the star, and then gradually coming in closer before settling into a stable orbit. Planetesimals formed by many collisions taking place, accreting and sticking together until larger and larger worlds were formed. Over time, as planetesimals grew, the denser material would sink to the center, just like heavy material sinks to the bottom of anything that is once homogeneous. This is due to the effect of gravity. Eventually, a differentiated world would contain the heaviest things, such as iron, in its core, and the lighter rocks surrounding it. Atmospheres can be explained in one of two ways. Most likely, they were formed by a combination of both of these mechanisms. Outgassing occurs when volcanic activity releases gases, and collisions are also responsible for gas being vaporized into the atmosphere. However, once an atmosphere forms, that doesn't mean that the planet will be able to hold on to that atmosphere. Indeed, the planet Mars is on the edge of what is known as the habitable zone of our solar system. But unfortunately, Mars is a very small planet compared to the Earth, and as such has lower gravity. Lower gravity means less gravitational force to hold on to the atmosphere. Most of Mars's atmosphere, if there was one, likely escaped to space. And thus Mars is left with a very thin atmosphere. Think of it as a blanket. The stronger you are, the more you are able to hold on to your blanket if somebody tries to pull it off of you, and the warmer you stay. Mars was only able to hold on to a very thin blanket, rendering its surface temperature very cold. Now let's think of the Earth as a terrestrial planet of the solar system. What do we know about the composition of the Earth? Well, we know that its surface is comprised mostly of silicon and oxygen. It is more difficult to determine what is deep within the Earth, because drills could not possibly go that deep. Earthquakes help us to figure out the interior of the Earth by proxy. Here's a breakdown of the elements which comprise the crust of the Earth. Earthquakes generate waves that react differently whether they are traveling through rock or liquid. S waves really can only travel through rock, whereas P waves can travel through both, liquid or rock. When the S waves travel from earthquakes, they can travel through the rocky parts of the Earth, but not through the liquid core. Thus, a shadow presents itself, implying that somewhere deep within the Earth there exists very hot liquid. This is basically a cutout of the interior of the Earth as best we understand it. At the very center, you have a solid iron and nickel core, surrounded by a liquid iron and nickel core. Then you have the mantle, which is comprised mainly of liquid rock, molten rock. And then you have the very thin crust. The crust is almost like an eggshell surrounding an egg. It's extraordinarily thin. The interior of the Earth is still hot from its days of formation and is only slowly cooling down. The core temperature of the Earth is thought to be around 6,500 Kelvin, which is as hot or hotter than the surface of the Sun. This very hot core creates convection currents, and these are in turn what drive the motions of the crust through plate tectonics. As the convection currents move, they drag the crust along with it. In some places, this results in subduction zones, with part of the crust sinking below another part, or rifting, where new ocean floor is being formed, such as in the Atlantic Ocean. In other places, plate tectonics have slowly been moving the continents around over millions of years. If you've ever thought that South America and Africa look as though they fit together like pieces of a puzzle, this is most likely because over 200 million years ago they were together. Even today, the continents are still drifting. India is still pushing up the Himalayas, and the United States is still moving farther away from Europe, about 2 centimeters every year. Earth also has a magnetic field. This is good for us because the magnetic field directs charged particles away from us. Every few thousands of years, the magnetic pole flips and north becomes south and south north. We are overdue for such a flipping. However, Be advised that this is not a drastic, sudden change, but gradually, over time, the North Pole will migrate to the south.